Hello everyone, welcome to this material characterization online course organized by NPTEL. In the last class, we have just looked at some of the basic definition of quantitative microscopy, and then I just mentioned that the parameters which are used to quantify the microstructures, namely volume fraction and grain size and etc. So, I stopped the first tutorial with the definition of ASTM grain size and also the equivalent grain size number G. So, I will just continue that tutorial class. I will just work out some of the numerical problem to give you a feel of how to calculate an ASTM grain size number using those formulas which I mentioned. So, what is this problem says? If the problem is an ASTM grain size determination is being made on a photomicrograph of a metal at a magnification of 100 times 100x. What is the ASTM grain size number of the metal if there are 64 grains per square inch? So, how to approach this problem? So, let us look at the formula what we have written for the ASTM grain size. This is a formula. So, where grains per square inch at 100x and NAC ASTM grain size number. So, this is what we have stated in the last class. So, now you have since 64 grains per square inch, that means you have the small n available. So, that means 64 grains per inch square is equal to 2 power n minus 1. Now, you just solve this, that is log 64 is equal to n minus 1 into log 2. So, this is 1.806 is equal to n minus 1 into 0.301. So, n is approximately 7. So, that is the answer. So, very simple substitution, you can find out easily from this formula. So, we will look at another formula, another problem, just to illustrate the application of this equation. If there are 60 grains So, the problem is, if there are 60 grains per square inch on a photomicrograph of a metal at 200 x, what is the ASTM grain size number of the metal? So, what is the difference between the previous problem and this problem? There we had number of grains per square inch was given at 100 x, here it is given at 200 x. So, how to go about it? So, again we will write this n is equal to 2 to the power minus n minus 1. So, if there are 60 grains per square inch at 200 x, then at 100 x we will have 200 by 100 is equal to 240, which is equal to 2 to the power n minus 1. So, what you have to do is, instead of what you have is 200 x, so you have to convert that into 100 x by this method. So, you have this, which is 240, then from there it is again straightforward. You calculate log 240 is equal to n minus 1 log 2 and 2380 2 point m is equal to 8.91. So, remember here we are talking about this capital N, not a small n. So, even in the previous problem there is a correction, it is we are considering capital N as the ASTM grain size number, because this is what we are trying to find out. So, you should not confuse these things. So, capital N is equal to 8.91. So, here you write what is that you are learning from this problem? The ratio of the magnification change must be squared. Since we are concerned with number of grains per square inch. So, what is that you have to learn from this problem? This is the only difference we have made. So, the ratio of the magnification must be squared, since we are interested in the number of grains per square inch. So, that is the only difference between the previous problem and this problem. So, that is how it is done. So, what you have to appreciate by just looking at the grain size number, we can just write some general from these problems. What is that we have learned? We have just learned to compare the grain sizes in terms of a reference called ASTM grain size. So, we can say that if ASTM grain size N is less than 3 and it is classified as coarse grained. If N, suppose N is between 4 and 6, it is medium grain. If it is between 7 and 9, it is fine grained. If you have N is greater than 10, it is called ultra fine grained. So, this is a general reference which is quite handy when you look at the ASTM grain size charts. If it is less than 3, coarse grain. If it is between 4 and 6, medium grain. If it is between 7 and 9, it is fine grained. If it is greater than 10, it is ultra fine grain. So, that gives a ready reference. But then we can also look at some of the, as I mentioned, we can look at some of the direct measurement of grain size, direct approach. of assessing grain size which is sometimes referred as D C divided by n L times first we will write what is D. D is equal to average grain diameter. C will have sometimes 1.5 for typical measurements and M is magnification. So you can write here number of grains intersected random line of no length and the ratio of number of grains to the So this is a direct approach, one of the direct approach. I will also give another method of measuring directly like this. This is one of the methods where T is the average grain size diameter and C is a constant, typically 1.5 for most of the microstructures. M is magnification. So the number of grains intersected by a random line of known length and the ratio of the number of grains to the actual length of the line is determined NL, then the diameter of the grain is related like this. This is about measuring the grain size, and we can also look at one more simple formula or a problem, one more problem we can solve before we move on to the next parameters. 3 A determine ASTM grain size number So, this is a similar problem what we have solved previously. In fact, the two separated problem has been combined into the single problem, but numbers are different. I hope you can all solve by yourself. Let me read the problem. Determine the ASTM grain size number of a metal specimen if 55 grains per square inch are measured at 100 magnification. For the same specimen, how many grains per square inch will be there at 85 magnification? So you have to just follow the similar procedures like what we had done previously. Nevertheless, I will just complete this for the sake of your comfort. So, okay, let us use this n minus 1 log 2 and solving is equal to log n divided by log 2 plus 1. So, here log 45 log 2 plus 1 is equal to 6.5. So, this is about ASTM grain size number. In part B, you have to just recast the formula like Nm m by 100 whole square 2 into the power minus 1. So, this is how you can recast this formula for a different magnification. Then you simply substitute this. So, in this expression Nm number of grains per square inch at m, at magnification m. So, then now you know why we do this, because we are interested in number of grains per square inch. So, that is why this term comes. So, now you just substitute this simply in this expression. So, you write two to 6.5 minus 1 times 100 by 85 square, which is equal to 62.6 grains per square inch. So, what I have done is from this formula I have substituted this. We are interested in this, so this will go that side and then it will be like this. So, you get the answer 62.6 grains per square inch. So, this is how you should carry out these problems. So, first we have seen grain size. I will now talk about surface area of grains. Of So, what we are now talking about is surface area of grains. The parameter called the surface area per unit volume SV of grain boundaries, and the constituents is calculated from the mean linear intercept L, mean linear intercept L, which we talked about in the linear analysis, which is measure of again grain size using this relation SV is equal to 2 by L, or you can, it is 2 times the number of intercepts per unit length. So, this is surface area per unit volume, you have to remember SV. So, this expression is valid for any space filling arrangement of grains. And it is independent of the shape disposition of microstructural features So, this expression is valid for any space filling arrangement of grains, and it is independent of the shape and disposition of microstructural features, provided that the plane section is truly random. So, the 2D section which we make to measure this should be a random section, and then this expression is valid. So, we can also relate this expression with something else, the number of grains per unit volume NV is related to SV by K in V to the power 1 by 3. K is constant related to grain shape which is for equiaxed grains K is approximately equal to 8 by 3. So, this is the other parameters which can also be found out from the linear analysis parameter what you get, which is also a very powerful parameters. And then the other quantitative measure where the optical micrography is useful is inclusion counting. So, this is very specific to metallic samples, especially the unwanted material, so called dirt you can say, for people who are not aware of the or not familiar with this inclusion rating or inclusion counting, especially in steels, is very important. So, this is again done using this optical micrography with some of the methods. The other one is particle size and spacing. The mean free distance of particles that is the average edge to edge distance. Distance of the particles is given by lambda is equals one minus VV where VVP volume fraction of particles NL, number of meters. So, what I have written is the mean free distance of particle lambda, that is an average edge to edge distance of the particles, is written as lambda is equal to 1 minus VV, volume fraction of the particle, divided by NL, where NL is the number of particles interceptions. So, it is not intersections, it is interceptions per unit length of the test line. So, you can just we know how to calculate this, we can do by point counting, and this is obtained by counts of number of particles intersected by random straight lines. This also we have seen how to do that. So, the mean spacing is given by sigma is equal to 1 by n. So, clearly when so, there we have seen that particle size spacing, and here the mean random spacing sigma, that is a mean center to center spacing, is given by sigma is equal to 1 by NL. We know what is NL. So, clearly from these two expressions what you can see is when the particle becomes very small, so the lambda tends to become sigma. So, the mean intercept length LP, that is otherwise it is nothing but a mean particle diameter is given by LP is equal to sigma minus lambda, which is nothing but volume fraction of the particle divided by the NL, which is the number of particles interceptions per unit length. So what we are trying to say here is a simple measurements from an optical micrograph or any photomicrograph, a simple point counting or a line intercept counting will give you very effective and very powerful, very effective way of measuring quantitative parameters. They are very powerful techniques. So, one has to just appreciate and realize this. So, I will show some of these expressions used to evaluate the quantitative data from a simple optical micrographs or an ACM micrograph in the coming classes. So, but what I have just given is very brief and an elementary quantitative microscopy. The subject itself very huge, and it has got a lot of applications. Complete statistics and mathematical relations are involved. But an application of optical microscopy, if you are familiar with this basic or in elementary relations, you will be able to derive an important quantitative parameters like volume fraction or particle size, particle spacing or grain size and so on. So, that is why I just introduced these concepts. In the coming 2-3 tutorials, I will just demonstrate these techniques, how it is done on an actual micrograph, and you will able to appreciate the usefulness of these expressions. I will also give you some more practical exercise for you to do it at your end to get familiar with this kind of techniques. Thank you.